Welcome to lecture 4 on inverse trigonometric functions. In the last lecture, we had derived some relations between these inverse trigonometric functions. So, we will conclude with that and we will solve some new problems. So, just to recap where we left from. So, in the last lecture, we had actually derived this formula for the sum of the tan inverses of two different values x and y, and we had shown that if the product x y is less than 1, then tan inverse x plus tan inverse y is tan inverse of x plus y over 1 minus x y, and similarly for the other two cases. So, a natural question then which can be asked is, what if we have to compute something like sine inverse x plus sine inverse y? Will it be possible to use the tan inverse A plus tan inverse B type formula and derive the value of sine inverse x plus sine inverse y? And that is possible. So, the way to do that would be to first convert, for a given x, to convert sine inverse x into the form tan inverse of something, where this something would obviously depend on x, and similarly convert sine inverse y also into tan inverse of something. So, then we just have to compute tan inverse A plus tan inverse B, for which we can actually use this formula. So, taking that idea forward, we had in the last class derived the conversion formulas between sine inverse and tan inverse. So, what we had shown was that for any x such that mod of x is less than or equal to 1, sine inverse x is equal to tan inverse of x upon square root of 1 minus x square, where this is the positive square root, and the reverse formula was for any x real. We had also shown that tan inverse x is equal to sine inverse of x over square root of 1 plus x square, where this is again the positive square root. So, just like the conversion between sine inverse and tan inverse, it is also possible to derive the conversion formulas between cos inverse and tan inverse, between cot inverse and tan inverse, and also between cosec inverse and tan inverse, and between sec inverse and tan inverse. So, in the interest of time, we are not going to derive all of them, but I will at least go ahead and derive the conversion formula between cos inverse and tan inverse. So, the idea is that suppose if we are given a value of x, which is whose modulus is less than or equal to 1, then we need to find this unknown value here such that cos inverse of x is equal to tan inverse of this value. So, this is what has to be derived. So, we start with by saying that suppose cos inverse x is equal to theta, then since the range set of the cos inverse function is the closed interval 0 to pi, it follows that this theta must belong to the closed interval 0 to pi. Now, suppose that if x is greater than or equal to 0. So, we are going to take two cases. So, x is either greater than or equal to 0 and less than 1, or it is less than 0 but greater than minus 1. So, if x is greater than or equal to 0, then from the graph of cos inverse, which we have already done in one of the previous lectures, we know that the theta has to belong, theta is cos inverse of x, theta has to belong to the interval 0 to pi over 2. Since we want to find this unknown thing, if you apply tan function on both the sides of this equation, what you will get is tan of cos inverse x is equal to this unknown thing that we are supposed to find. So, that is why we try to find the value of tan of cos inverse x, which is tan of theta, but from here we know that x, if we take cos, if we apply the cos function on both the sides of this equality, what we are going to get is x is equal to cos theta. So now this tan theta is equal to sin theta over cos theta, but cos theta is x, so the denominator is x. Now when theta belongs to the interval 0 to pi by 2, we know that sin theta is positive valued. So therefore we can write it sin theta as the positive square root of 1 minus cos square theta. Of course, this follows from the fact that sin square theta plus cos square theta is equal to 1 for any theta, and we take the positive square root here, which is further equal to square root of, now we use the fact that cos theta is actually x, so this becomes square root of 1 minus x square over x. And further, so finally what we get is that if x is greater than or equal to 0, then tan of theta, where theta is cos inverse x, is equal to square root of 1 minus x square over x. We further know that this theta actually belongs to the interval 0 to pi by 2, and this interval 0 to pi by 2 is actually a subset of the interval minus pi by 2 to plus pi by 2. So essentially the interval 0 to pi by 2 to which this theta belongs is actually a subset of the range set of the tan inverse function. So because theta, so essentially theta belongs to the, so theta belongs to the range set of the tan inverse function, and because theta belongs to the range set of the tan inverse function, it follows that theta, which is actually cos inverse x, is equal to tan inverse of square root of 1 minus x square over x. But this is only true for x greater than or equal to 0. So again repeating it, the reason why, so this, for if theta were not belonging to this set, then from starting from this statement we cannot say that this is true. So the only reason we say that theta is equal to tan inverse of this quantity, the reason why that is true is because theta is belonging to the range set of tan inverse, range set of tan inverse. And then we take the negative values of x. So if x is less than 0 and of course greater than or equal to minus 1, then we know that theta equal to cos inverse x will belong to the interval pi by 2 to pi. So this follows from the definition of the cos inverse function, because x is between minus 1 and 0, theta will obviously belong to the interval pi by 2 to pi. And then tan theta will be equal to sin theta over cos theta, which is equal to, again, now in this interval when theta belongs to pi by 2 to plus pi, what we have is that sin theta is still positive, so we can express sin theta as the positive square root of 1 minus cos square theta over cos theta, but we already know that cos theta is x, so this becomes equal to square root of 1 minus x square over x, where this is the positive square root. So we again have tan theta equal to square root of 1 minus x square over x, but this time we know that because x is negative, theta equal to cos inverse x, it belongs to this set pi by 2 to pi, but the problem is that this set is not a subset, or this set does not have any point in common with the range set of tan inverse. So, essentially here we have a case that if theta belongs to this set, then theta does not belong to the range set of tan inverse, and therefore we cannot write. So, we cannot write that theta is equal to tan inverse of square root of 1 minus x square over x. So, for this case where x is negative, this statement is not true. So, this statement is not true, and therefore, we need to apply some shift or some change to theta, so that after applying that shift, the new value of theta belongs to the range set of tan inverse. Now, we know from the property of the tan function that the tan function is periodic with a period equal to pi, and therefore, we know that if we subtract pi from this theta, essentially what we know is that tan theta is the same as tan of theta minus pi. And the good thing is that because theta belongs to the set pi by 2 to pi, theta minus pi will obviously belong to, so theta minus pi is going to belong to the set minus pi by 2 to 0, and this set minus pi by 2 to 0 is a subset of the range set of tan inverse. So, essentially what we have now is that theta minus pi is going to belong to the range set of tan inverse. So, if you go back, what we see is that the original theta did not belong to the range set of tan inverse, but by simply shifting it by pi, we have theta minus pi belonging to the range set of tan inverse. And since tan theta minus pi is equal to tan theta, what we have now is that, so tan of theta equal to tan theta minus pi is equal to square root of 1 minus x square over x. We know that theta minus pi belongs to the range set of tan inverse, and therefore, we can write that theta minus pi equals tan inverse of square root of 1 minus x square over x, which then implies that theta is equal to pi plus tan inverse square root of 1 minus x square over x, and therefore, but this then is only true when x is negative, and therefore, finally combining both the results for the positive and negative values of x, we finally have this conversion formula that cos inverse x is equal to, if x is greater than or equal to 0, then it is then cos inverse x is equal to tan inverse of square root of 1 minus x square over x. Otherwise, it is equal to pi plus tan inverse of square root of 1 minus x square over x. So, we next derive the reverse inverse relation, which is that for any given x real valued, tan inverse x is equal to cos inverse of something. So, we have to derive an expression for this something such that tan inverse x is cos inverse of this something. So, again we start with by substituting tan inverse x to be theta, and of course, theta has to belong to the open interval minus pi by 2 to plus pi by 2. So, this is the range set of the tan inverse function, and since we are interested in finding this unknown quantity here, we would actually be interested, because if we apply the cos function on both the sides of this equality, what we will get is cos of tan inverse x equal to this unknown thing. So, We are therefore interested in evaluating cos of tan inverse x, which is cos of theta, which is equal to 1 over secant theta. Now, when theta belongs to minus pi by 2 to plus pi by 2, secant of theta is non-negative valued, and therefore, we can write it as 1 over the positive square root of sec square theta, which can be further written as 1 over square root of. Now, we know the identity that for any angle theta, sec square theta is equal to 1 plus tan square theta. So, we are going to use this here. So, we write it as 1 plus tan square theta, and from here we know that x is equal to tan theta, because we applied tan function on both the sides. We get x equal to tan theta. So, this then is essentially 1 over root of 1 plus x square. So, we have cos of tan inverse x equal to this quantity. But from here, can we write that tan inverse x is equal to cos inverse of this quantity? So, well, we can only do that if we know that this value here, which is theta. So, cos theta is equal to this. So, we can only write that theta is equal to cos inverse of 1 over root of 1 plus x square. So, this is valid if and only if this angle theta belongs to the closed interval 0 to pi. So, the 0 to pi is actually the range set of the cos inverse function. So, only if this theta belongs to the range set of the cos inverse function, only then we can write theta to be equal to cos inverse of this quantity. Otherwise, we cannot write this. So, and this is not true in general in this case, because if you see theta here being in the falls in the range set of tan inverse, and therefore, it belongs to this set, and this set minus pi by 2 to pi by plus pi by 2 is definitely not entirely contained in the range set of the cos inverse function. So, therefore, we cannot say that always, we cannot always say that theta, which actually belongs to this set, will also belong to this set, because these two sets, I mean, because this set minus pi by 2 to plus pi by 2 is not contained within the set 0 to pi. So, therefore, we divide the problem, this problem into two cases. We first take the scenario where x is greater than or equal to 0, because when x is greater than or equal to 0, then we know from the graph of the tan inverse function that tan inverse theta equal to tan inverse x. So, theta is going to therefore belong to the set 0 to pi by 2. So, when x is greater than or equal to 0, theta equal to tan inverse x belongs to the interval 0 to, so this will be the open interval. So, open from the open at pi by 2. And then now, since theta is going to belong to this, and we also know that 0 to pi by 2 is, of course, this particular set is a subset of 0 to pi. Now, this is the range set of the cos inverse function, and therefore, when x is greater than or equal to 0, theta belongs to the range set of cos inverse, and hence, since cos of theta is equal to 1 over square root of 1 plus x square, and theta belongs to the range set of cos inverse, it follows that theta, which is tan inverse x, will be equal to cos inverse of 1 over root of 1 plus x square. But this is only true when x is greater than or equal to 0, because when x is greater than or equal to 0, theta belongs to the range set of cos inverse, and therefore, from this equation we can straight away imply that theta is equal to cos inverse of 1 over the positive square root of 1 plus x square. We next take the other case where x is negative. Now, when x is negative, then theta equal to tan inverse x will belong to the set minus pi by 2 to 0. This is because this again is from the graph of the tan inverse function. But in this case, we clearly see that theta does not belong to 0 to pi. So, essentially in this case theta does not belong to the range set of cos inverse, and therefore we cannot conclude. So, therefore, in this case this statement will no more be true, because for the case of x negative our theta is not belonging to the range set of cos inverse, and therefore then we must try to shift this theta in such a manner that this theta belongs to the range set of cos inverse, but we should do it in such a way that the theta belongs to the range set of cos inverse. Now, we know that the range set of cos inverse is 0 to pi. So, if we increase theta by pi, so if we consider theta plus pi, first of all what we see is that if theta belongs to this set, then theta plus pi is going to belong to pi by 2 to pi, and this set is obviously a subset of the range set of cos inverse, and therefore although theta did not belong to the range set of cos inverse, but theta plus pi will. So, theta plus pi belongs to the range set of cos inverse. Additionally, cos of theta plus pi is equal to minus cos of theta, but we know that cos theta is 1 over square root of 1 plus x square. So, then this is equal to minus 1 over square root of 1 plus x square, where again this is the positive square root. So, cos of theta plus pi is equal to minus 1 over positive square root of 1 plus x square, and since theta plus pi belongs to the range set of cos inverse, we can immediately say that theta plus pi is equal to cos inverse of minus 1 over positive square root of 1 plus x square, and from here it can be concluded that theta is equal to minus pi plus cos inverse of minus 1 over positive square root of 1 plus x square. So, both these cases can be summarized now, and what we finally have is that for any value of x which is real valued, tan inverse x is given by this formula. So, when x is greater than or equal to 0, then tan inverse x. So, when x is greater than or equal to 0, then tan inverse x is equal to cos inverse of 1 over positive square root of 1 plus x square. But if x is negative, then tan inverse x is equal to minus pi plus cos inverse of minus 1 over positive square root of 1 plus x square. So, we just concluded with the conversion formula between cos inverse and tan inverse, and similar type of formulas can be derived between cot inverse and tan inverse. For example, if we are given cot inverse of x, we can convert that into something, an expression which consists of the tan inverse function like this. Vice versa, if we are given tan inverse of something, then that can also be alternatively be written as cot inverse of some other value. So, that is here, and further similar type of conversion formulas can be derived between tan inverse and cosecant inverse, and also between tan inverse and secant inverse. So, the primary use of these formulas will be to help us in computing any general expression of the forms, sine inverse of x plus, let us say, secant inverse of y, or sine inverse x plus cos inverse y. So, the way to do that would be, as I mentioned earlier, that if we have to compute something like sine inverse x plus secant inverse y, then we basically convert, using the conversion formula, we convert this thing into tan inverse of some value, and using the conversion formula between tan inverse and secant inverse, we convert this to tan inverse of some other value. Note, of course, that this value here is a function of x, and similarly this value here is a function of y. And then we can use the tan inverse A plus tan inverse B type formula to write this in terms of tan inverse of some other value. So, this finishes our discussion on the properties of inverse trigonometric functions and the relations between these different inverse trigonometric functions. So, in the remaining part of this lecture and also in the next lecture, we are going to discuss several problems. So, here is the first problem. So, we are asked to compute the value of this expression, so which is cotangent of some angle, and that angle is sum of cot inverses of 23 different values. So, if we just look at this expression here, and let us try to derive that first. So, we have cot inverse of 1 plus summation k equal to 1 to n to k, which equals cot inverse of 1 plus. Now, this thing inside the summation is essentially 2 multiplied by and 1 plus 2 all the way till n, and that can be further simplified to 1 plus 2 times. Now, this thing inside the bracket is nothing but the sum of the first n natural numbers, which is equal to n times n plus 1 over 2. So, we therefore have this to be equal to cot inverse of 1 plus n times n plus 1. And suppose that we were to define, let us say that cot inverse of 1 plus n times n plus 1 equals theta, then of course we know that from the range of the cot inverse function that theta will obviously belong to the open interval 0 to pi, which is the range set of the cot inverse function. Then applying the cot function on both the sides of applying the cot function on both the sides of this equality, we get cot of theta equal to 1 plus n into n plus 1, and therefore tan of theta equals 1 over 1 plus n into n plus 1. And this expression here is nothing but can also be simplified to n plus 1 minus 1 minus n plus 1 minus n over 1 plus n plus 1 into n. So, this expression over here reminds us of the formula tan of x minus y equals tan x minus tan y over 1 plus tan x tan y. So, here essentially this n plus 1 is tan x, n is equal to tan y, and then if we use that substitution, then we basically get this expression here. So, therefore, we can write this whole thing tan theta also as equal to tan of tan inverse n plus 1 minus tan of tan inverse n over 1 plus tan of tan inverse n plus 1 times tan of tan inverse n. So, this is of the form tan x minus tan y divided by 1 plus tan x times tan y, which is, but this is nothing but tan of. So, here this is our x and this is y. So, x is tan inverse of n plus 1, y is tan inverse of n. So, therefore, what we get is that tan theta is, so this essentially is, this whole expression here is nothing but tan of x minus y, where x is equal to tan inverse of n plus 1 and y is equal to tan inverse of n. So, we get tan theta to be equal to tan of x minus y, which is tan inverse n plus 1 minus tan inverse of n. So, this is what we have got so far. Further, we also know that because this n are natural numbers and these n are also, and therefore, all n and n plus 1 are greater than 0, and therefore, it follows that since n and n plus 1 are greater than 0, it follows that tan inverse n plus 1 must belong to the interval 0 to pi by 2, and similarly tan inverse of n must also belong to the interval 0 to pi by 2. And further, and therefore, it is clear that their difference tan inverse n plus 1 minus tan inverse of n must belong to the interval minus pi by 2 to plus pi by 2. And remember that this is nothing but the range set of the tan inverse function. So, essentially what we have here is that, if you remember when we started with, we had, so here we initially had that theta will belong to 0 to pi, because this is what is the range set of cot inverse. But we now further know that tan theta is positive, and therefore, adding this fact along with the fact that theta must lie in the interval 0 to pi, what we can say is that theta must therefore belong to the interval 0 to pi by 2. So, this is because tan theta is positive value, and additionally the fact that theta must belong to 0 to pi. So, if we look at the graph of the tan function, so this is from one of the previous lectures. So, we see that, so this is the value of tan x is on the vertical axis and x is on the horizontal axis. So, the curve in the marked with blue is the curve for the tan x function. So, as we can see here, whenever x is between 0 to pi by 2, the value of tan x is positive. But then between pi by 2 and pi, the value is this value here, this part of the curve here, this is negative. And we are said that the theta is going to only belong to this interval, only from here to here. And further, we know that tan theta must be positive, and therefore, it is clear that theta must belong to this interval 0 to pi by 2. So, we know that theta must belong to 0 to pi by 2. So, so let us focus on this equation now. So, theta must belong to 0 to pi by 2, and additionally this difference angle here, we just showed that this angle also belongs to minus pi by 2 to plus pi by 2. But if we remember the graph of the tan inverse function, so this is the graph of the tan inverse function. So, we have x on the horizontal axis and tan inverse x on the vertical axis. Now, we can clearly see that the tan inverse function is a monotonically increasing function. It has been plotted in red. So, it is a monotonically increasing function, and therefore, because n plus 1 is greater than n, it obviously follows that tan inverse of n plus 1 will be greater than tan inverse of n. And from here we can easily say that, therefore, using this fact in our previous equation, we can say that this quantity over here is, so this quantity here is greater than equal to 0, and further we know that in fact it should be strictly greater than 0, because n plus 1 and n can never be the same. And further we had shown that this entire value has to belong to this set, and therefore, by combining this fact with the fact that this value belongs to this set, we can also tell that the value tan inverse n plus 1 minus tan inverse n must belong to the interval 0 to pi by 2. So, now what we have is that we have a situation where tan theta equal to tan of tan inverse n plus 1 minus tan inverse n. We know that theta must belong to 0 to pi by 2, the open interval, and we also know that this value tan inverse n plus 1 minus tan inverse n should also belong to the same interval, same open interval 0 to pi by 2, and these two values tan of theta and tan of this angle are the same. Now, because we know that again going back to the curve for the tan function, we know that in the interval 0 to pi by 2, as we can see, the tan function is a monotonic function, it is a monotonically increasing function, and therefore, let us say that if this is theta, then this value over here is tan of theta. Since tan is a monotonically increasing function in the interval 0 to pi by 2, it follows that if tan theta were to be equal to tan of this angle, the only way that is possible is if theta itself is equal to tan inverse of n plus 1 minus tan inverse n. So, this is what must be true, and therefore, what we have shown so far is that cot inverse of 1 plus n into n plus 1 is actually equal to tan inverse of n plus 1 minus tan inverse of n. And then further going ahead, we saw that we have just simplified one of the terms of this outer summation. So, now if we replace all these terms by this expression, so this summation will turn out to be summation of n equal to 1 to 23 cot inverse 1 plus summation k equal to 1 to 2n 2k is equal to summation n equal to 1 to 23. Now, if we replace all these cot inverses by the expression tan inverse n plus 1 minus tan inverse of n, but then if we just expand this big summation, we will, starting with n equal to 1, the first term is tan inverse 2 minus tan inverse 1. The second term is tan inverse 3 minus tan inverse of 2, and likewise the last term is going to be tan inverse of 24 minus tan inverse of 23. But what we are going to see here is that there is going to be a lot of cancellations. For example, tan inverse 2 will get cancelled here, and similarly tan inverse 3 will get cancelled with because the just previous term here, the 22nd term in the summation is going to be tan inverse 23 minus tan inverse of 22. So, this minus tan inverse will get cancelled here, and then similarly minus tan inverse 22 will get cancelled with the tan inverse 22 in the 21st term. So, and similarly this will also get cancelled from with the tan inverse 3 in the third term. So, ultimately what is going to remain is tan inverse of 24 minus tan inverse of 1. And to compute tan inverse of 24, so therefore, we finally have to compute essentially what we have done so far is that we have shown that cot of summation n equal to 1 to 23 cot inverse of 1 plus summation k equal to 1 to 2n of 2k. So, we have shown that this thing inside in the argument of the cot function, we have shown that that is equal to tan inverse of 24 minus tan inverse of 1. So, now we need to simplify this further, because the idea should be to actually express this whole thing as tan inverse of something, so that we can then have cot of tan inverse something, and then we have already seen this conversion formula between cot and tan. So, that should help us. So, for this thing we, if you remember in the starting of this class today, we were actually revisiting some of the earlier derived results. So, one of the results was this expression here, that tan inverse x plus tan inverse y is equal to tan inverse of x plus y over 1 minus xy if xy is less than 1. So, in our case what is happening is that we need to compute tan inverse of 24 minus tan inverse of 1, which can, now because the tan inverse is an odd function, I can write minus tan inverse of 1 as plus tan inverse of minus 1. This is because the tan inverse is an odd function. What I mean to say is that for any x, tan inverse of minus x equals minus of tan inverse of x. And we have shown this identity in a previous lecture. So, now this term therefore equals to tan inverse of 24 plus tan inverse of minus 1. So, finally, we have this expression in the form tan inverse x plus tan inverse y. So, this is x and this is y. And then here we see that x into y is minus 24 and minus 24. So, out of all these cases, the case that we have at hand is x y equal to minus 24, which is less than 1. So, we have to use this case here, and therefore, this expression will be equal to tan inverse of x plus y. So, x plus y is minus 1 divided by 1 minus x into y. So, x is 24 and y is minus 1. So, this is the final answer. What we get is tan inverse of 23 over 25. So, therefore, now what we have is that this is equal to tan inverse of 23 over 25, and hence this whole thing is equal to cot of tan inverse of 23 by 25. So, the final answer will be cot of tan inverse of 23 over 25. And this can also be simplified further, because now suppose let us say that tan inverse of 23 by 25 is theta, then obviously it follows that 23 by 25 is equal to tan of theta, because we can take apply the tan function on both the sides of this equality of this equation, and then we get this thing. But from here it follows that cot of theta is equal to 1 over tan theta, which is 25 over 23. but then this is nothing but cot of theta, because theta is tan inverse 23 by 25, and now we have just seen that this is exactly equal to 25 over 23. So, this is the final answer, that cot of this big summation is equal to 25 over 23. Let us take one last problem before we conclude this lecture. So, here, we have to find a value of x such that mod of x is between 0 and square root of 2, and that x satisfies this trigonometric equation. So, before we proceed further, we see that there are two infinite series. So, we need to simplify them, and then maybe we can go further. So, we take the first series which is inside the sine inverse. So, the first series is x minus x square over 2 plus x cube over 4 minus, so most likely the minus x 4 over 8 plus and so on. So, we can take x as the common factor outside, and then we get 1 minus x over 2 plus x square over 4 minus x cube over 8 and so on. And that can be written as x times 1 plus minus x over 2 plus minus x over 2 whole square plus minus x over 2 cube and so on. So, immediately we see that we have a geometric series over here, and then we need to find out whether this series is going to converge or not. So, we are given that, if we go back to the statement in the question, we are given that mod of x is less than square root of 2. So, if mod of x is less than square root of 2, that implies that mod of x has to be also less than 2, which then implies that mod of x over 2 is less than 1, and that also means that mod of minus x over 2 is also less than 1. So, we see that the ratio between this term and the next term, and also between this term and its next term, is minus x over 2, and from here we know that minus x over 2 has an absolute value which is less than 1. So, that basically from there we can conclude that this series is going to converge, and it will converge to the value. So, we already have this x from here, and then this series is going to converge to 1 upon 1 minus x over 2, which is x upon 1 plus x over 2. So, now we know that this infinite series is equal to x upon 1 plus x over 2. Next we take the other series which is inside the argument of the cos inverse function. So, this other sequence which is the argument of the cos inverse function is x square minus x 4 over 2 plus x 6 over 4 and so on, which can be written as x square, since x square is common to all the terms, times 1 minus x square over 2 plus x 4 over 4 and so on, which is equal to x square times 1 and then plus minus x square over 2 plus minus x square over 2 whole square and so on. So, even in this case we see that there is again another geometric progression, and but we still need to find out whether this infinite sequence is also going to converge or not. Now, we are given that mod of x is less than square root of 2. So, what that implies is that x square is less than 2, and therefore, x square over 2 is less than 1, and this basically implies that the modulus of minus x square over 2. So, minus x square by 2 is the ratio between the nth term and the n minus 1th term in this geometric series, and from here we know that the absolute value of this ratio is less than 1, and therefore, even this sequence is going to converge, and therefore, this whole expression, this whole sequence is going to converge to the value x square times 1 upon 1 minus x square over 2, which is equal to x square upon 1 plus x square over 2. So, let us make a note of that. So, what we have shown just now is that this other sequence also in the argument of the cos inverse function converges to x square upon 1 plus x square upon 2. We next have to find values of x such that mod of x is less than square root of 2 and sine inverse of x upon 1 plus x by 2 plus cos inverse of x square upon 1 plus x square by 2 is equal to pi by 2. So, let us denote this thing by alpha and the other term which is the argument of the cos inverse function by beta. So, essentially what we have here is that sine inverse alpha plus cos inverse beta is pi by 2, and that is the same as saying that sine inverse alpha is equal to pi by 2 minus cos inverse beta. Now, let us apply the sine function on both the sides of this equation. So, when we apply sine to the left hand side, we get sine of sine inverse alpha, which is equal to alpha. On the right hand side, we get sine of pi by 2 minus cos inverse beta. But we know that for any angle theta, sine of pi by 2 minus theta is equal to cos of theta, and therefore, this right hand side is equal to cos of cos inverse beta, which of course is equal to beta. And therefore, if x has to satisfy this equation, this must be equal to this. Hence, what we finally have that is that x must satisfy the equation x upon 1 plus x by 2 equals x square upon 1 plus x square over 2. Now, since mod of x is less than square root of 2, it follows that both these denominators will never be 0, and therefore, from here it implies that x into 1 plus x square over 2 equals x square into 1 plus x over 2. And then with a little algebraic simplification, we get x plus x cube over 2 equals x square plus x cube over 2. And of course, x cube over 2 is on both the left and the right hand side, and hence what we finally get is that x into x minus 1 equals 0. So, x can be either 0 or it can be 1, but if we go back to the question, it was also stated that mod of x must be greater than 0 and it must be strictly less than square root of 2. Since it must be strictly greater than 0, x equal to 0 is obviously not a feasible solution, and therefore, the only feasible solution is x equal to 1, because x equal to 1 is the modulus of x equal to 1 is less than root 2, and also that x equal to 1 satisfies this equation. So, the final answer to this question is that the only value of x with modulus less than root 2 is, and which also satisfies this equation, is x equal to 1. So, the final answer is x equal to 1. So, with that we will end this lecture. In the next lecture, we will take up some more interesting problems. Thank you.